Welcome back to Dead Reckoning, the Human Life Expectancy channel. If the Dead Reckoning framework can help us to focus on death, perhaps it can also help us to muster the courage to focus on sex and human reproduction as well. In our video, Is Evolution Evolving?, we highlighted that from a biological perspective, the human reproductive process is inefficient and simply doesn't work for many people who want to become parents. In the US, the natural fertility rate is only about 20%. That is, it takes the average healthy, fertile couple 5 months of trying to successfully conceive, and about 1 in 8 couples experience fertility issues. And this is likely to get even worse in the future. Not only has the male sperm count fallen by 59% since 1973, as we covered in our video, How Will the Population Growth End? In addition, as women put off having children to later ages, the ticking of their biological clocks will likely get louder. Women's fertility declines sharply in their 30s and 40s, and very few are able to give birth with their own eggs in their late 40s and early 50s. The good news is that over 90% of infertility cases can now be overcome with medical treatments. To get around these problems and allow couples to have more children, to date, about 8 million people around the globe have been born using a process called in vitro fertilization, IVF, where eggs are fertilized in test tubes or culture dishes. Vitro means glass in Latin. And then they're medically implanted for gestation and birth. This is still a small number compared to the 140 million new babies born each year, but IVF is growing rapidly. Currently, there are about 3 million IVF births per year, or about 2% of overall births around the globe. In addition, in this video, we'll see that genetic and epigenetic testing, together with our increasing ability to create egg cells from skin cells or any other cell, are poised to revolutionize human reproduction and cause this number to grow dramatically. Look, there's no avoiding it. This topic raises multiple ethical issues about which many feel quite strongly. Since how we feel about anything should be driven by the facts of what it actually is, in this video, we'll explore the facts of what IVF is today and what it could become with these new medical and technological advances. And most central to our thesis, we'll also explore how it might impact global HLE going forward. In future videos, we'll address related ethical issues directly, with the intent of sparking dialogue that will ultimately help us to grapple with these new reproductive possibilities. For now, we simply note that after decades of helping couples to have children, the current IVF process is allowed everywhere around the globe, except for Costa Rica, which bans it to protect the perceived rights of human embryos. So what is IVF, and how is it used today? Couples are increasingly turning to IVF to overcome a broad range of conditions that can reduce fertility. In short, IVF can solve many of the problems associated with ensuring that healthy sperm fertilize healthy eggs and are successfully implanted in the womb. However, IVF is currently an arduous, painful, and expensive process. The process commonly involves 7 steps that takes about 4 months. Step 1 is 3 months of preconception health regimen and fertility testing for both the mother and the father to ensure that the IVF process is actually necessary. In Step 2, the mother takes oral contraceptives for 1 to 14 days to stimulate egg growth in her ovaries. Then, in Step 3, the mother undergoes 9 to 11 days of fertility medicine injections to prepare her womb to receive the embryos. It involves visiting the doctor every day or 2 for vaginal ultrasounds and blood testing. In Step 4, the mother undergoes a surgical procedure to retrieve healthy eggs from her ovaries. This is a 1-day procedure involving anesthesia, and while complications are rare, resulting in hospitalization in only about 1% of the time, some postoperative pain is actually common. Step 5 is a 5-day period where the eggs are fertilized and allowed to grow to the blastocyst stage, where the chances of healthy implantation are greatest. During this time, they grow from about 16 cells to about 200 to 300 cells. For comparison, the average housefly has about 500,000 cells, and the average adult human has 37.2 trillion cells. Blastocysts possess an inner cell mass, which subsequently becomes the embryo. The outer layer of the blastocyst consists of cells collectively called the trophoblast that ultimately become the placenta. In step 6, the mother and father, with the counsel of their doctors, select blastocysts for implantation. Since the process can take several days, the blastocysts are commonly frozen to allow the necessary time for testing and selection. Studies have found that the testing, freezing, and unfreezing of blastocysts does not reduce the success rate of implantations or the health of the resulting infants. Finally, in step 7, selected blastocysts are then unfrozen and implanted in the mother's womb for gestation. Blastocysts that were not selected are commonly kept frozen for potential future use. The doctor implants them in a relatively simple one-day procedure that typically doesn't involve anesthesia. Since not every blastocyst successfully implants, typically more than one is usually implanted. One consequence of this is that the rate of fraternal twin births has just reached an all-time high around the globe. Step 7 ends after an additional 9 to 10 day period to see if the blastocysts implant in the uterus. In the end, the first cycle of IVF costs $12,000 to $15,000 and only has a success rate of 40% for women under 35 and only a 4% success rate for women over 42. The fact that millions of couples are willing to go through this process, endure the pain, and pay the costs is testament to the strength of our drive to have children. We suspect that this is unlikely to change and that many might welcome future improvements to IVF. So, what could IVF become? 2 new technologies are poised to take this to a whole new level. First, recent advances in genetic and epigenetic testing that we explored in our last video will allow us to know ever more about the embryos that might be implanted in IVF, allowing parents much more visibility and choice in who their children will be. Again, we'll discuss the very real ethical issues of whether parents should have such rights, and if so, what their proper dimension should be in future videos. For now, let's acknowledge that parents have been choosing the attributes of their children for eons, albeit less directly, by their choice in mates. And since the 1950s, amniocentesis and other diagnostics have been used in prenatal diagnosis of chromosomal abnormalities and fetal infections, as well as for sex determination as a part of prenatal care. When genetic and epigenetic testing is applied to blastocysts, it's called Preimplantation genetic diagnosis, or PGD. PGD works by taking several cells from the blastocyst and sequencing their DNA using approaches we described in our last video. Medical studies have shown that PGD is safe and does not cause birth defects or developmental problems in the resulting children. As a matter of science, many attributes are discoverable today, and many more will undoubtedly be discoverable in the future. We can now screen for over 10,000 genetic diseases that are determined by single gene disorders, including sickle cell anemia, cystic fibrosis, Huntington's, Hodgkin's, and Parkinson's diseases, muscular dystrophy, Tay-Sachs, and even some types of cancers and diabetes. In addition, there's approximately 40,000 diseases that involve more than one gene, such as heart disease, many types of cancers, type 2 diabetes, Alzheimer's, and autism. Currently, we can screen for a range of such conditions, including diabetes, schizophrenia, dwarfism, late life osteoporosis, Alzheimer's disease, and colon, breast, and ovarian cancer. As the number of genetic sequences increases, we'll be able to screen for many more of these diseases. We can also scan for missing or extra copies of chromosomes. For example, Down syndrome is caused by having an extra copy of chromosome 21. Today, we can screen for sex and multiple physical traits, such as eye, hair, and skin color, nose shape, cheek dimples, male pattern baldness, strong bones, and even lean muscles. In the future, as testing technology improves and the cost of genetic testing decreases, researchers expect that we'll be able to screen for much more. Screening for more complex traits, such as height or intelligence, involves many genes and are more difficult to read from the genome, but should become possible. Most traits having a heritability of 50% or more could be predicted with relative accuracy once we have about 1 million people with their sequenced genomes and life records available, allowing us to do what's known as genome-wide association studies, or GWAS. One could easily imagine parents selecting their children to be taller, larger, stronger, and more physically able. Tall, strong men tend to get paid more, have an advantage in many sports, and arguably have more success with women. In addition, since recent evidence suggests that intelligence and IQ are 70% due to genetics, we should be able to select for this as well. How effective might this be? Carl Schulman and Nick Bostrom calculated that if embryos were selected for IQ, the difference between the highest and the lowest IQs could average over 25 points. Soon, we may be able to select for an even broader range of attributes: advanced abilities to see, hear, or sense, behavioral traits such as math ability, musical ability, or even personality type. Also, consider athletic ability. Athletes currently take steroids, growth hormones, testosterone, and many other substances to get an advantage and improve their performance. Selecting embryos that happen to be naturally gifted in these areas seems like a relatively small intervention by comparison. Also consider the ability to efficiently extract nutrients from foods. Lactose intolerance and gluten allergies could become a thing of the past. Parents might even be able to select for important capabilities such as sperm production or even the ability to endure hotter temperatures. On the other hand, using PGD to screen multiple blastocysts increases both the time and the costs required in IVF. Today it takes about 3 days of processing time to sequence a human genome. While the time required for sequencing will likely continue to shorten, the time required for parents to choose among the blastocysts is likely to be longer than this. Also, the cost of PGD is driven by the number of blastocysts tested, but typically costs an additional $3,000 to $5,000 at today's prices. This cost is widely expected to fall in the next decade as the volume increases. Moore's Law and other advances make this less of an issue, but it's likely to remain a barrier for lower-income couples around the world for some time. So, PGD is the first advance with the true prospect of revolutionizing human reproduction. A second advance could prove even more revolutionary. It's now become possible to create egg cells from skin or blood cells. This could greatly increase the number of eggs available to fertilize and reduce the cost and pain involved in retrieving them surgically. Here's the background. It was observed for many decades that since parents who possess highly differentiated cells are capable of producing sperm, egg, and stem cells, all of which are undifferentiated cells, there's got to be some mechanism for rejuvenating differentiated cells. If this weren't the case, parents would give birth to older offspring with even more differentiated cells, which of course is not the case. Then, in 1996, Keith Campbell, Ian Wilmot, and colleagues at the Roslin Institute used a process called somatic cell nuclear transfer to successfully clone Dolly the sheep from a mature cell from her mother's mammary gland. Dolly actually had 3 mothers. One provided the egg, another the DNA, and the third carried the cloned embryo to term. The mammary cell's nucleus was transferred into an unfertilized egg, which was then stimulated to divide by an electric shock. And when it developed into a blastocyst, it was implanted in a surrogate mother. Dolly's successful birth and life showed that genes in the nucleus of a mature differentiated somatic cell are capable of reverting into an embryonic totipotent state, creating a cell that can go on to develop into gametes such as eggs or cells, or any part of an animal. Later, in 2006, Dr. Shinya Yamanaka and his team discovered that proteins encoded by 4 master genes could transform any adult cell back into a stem cell. In effect, he was able to roll the epigenetic marbles back up the Waddington landscape we discussed in our last video into undifferentiated parent cells. He called these cells Induced Pluripotent Stem Cells, or iPSCs. In principle, this process can enable the development of an unlimited source of eggs or any type of human cell needed for therapeutic purposes. For this work, Yamanaka shared the Nobel Prize with John Gurdon in 2012. iPSCs have successfully been derived from people as old as 114 years, and the cells have an epigenetic age of 0, independent of the age of the donor. It also appears that this epigenetic resource is accompanied by other rejuvenative effects, including better mitochondria, lower reactive oxygen species, or ROS, and longer telomeres. Yamanaka's discovery offers the prospect of replacing IVF steps 1 through 4, which are responsible for the lion's share of IVF's current health risk, discomfort, and cost. As a result, many more blastocysts could be created, increasing the choices that parents have for implantation. Not only could this new process be used to help the infertile, it could also be used by gay or lesbian couples to have children of their own by making eggs from skin cells of men or women. Sperm cells have even been created this way for mice, and research for applying this to humans is ongoing. Again, we'll leave the discussions of ethical and social issues this might raise to future videos, and there's plenty of them. But for now, it's clear that this capability is emerging and could potentially become widely available in the future. Using iPSCs and PGD together can greatly expand the potential of IVF. Consider this. So far, we've discussed just selecting among one generation of blastocysts. But the iPSC technology allows us to breed pre-implanted blastocysts with each other, allowing for multiple generations of selection. This could be done by selecting 2 blastocysts using PGD for any preferred criteria, and then using iPSC to produce sperm and egg cells from those blastocysts to create another generation of blastocysts. These would be the genetic children of the first blastocyst and the grandchildren of the parents. This process could be completed as quickly as it takes for the new blastocyst to grow, which is only several days. The result would be that a mother could give birth to her own great-great-great-grandchildren, assuming the process was repeated 5 times, having had the opportunity to repeatedly select for specific criteria at each generation. This could dramatically speed up the process of human evolution, with up to 25 generations of evolution per year. Using such approaches, Stephen Su, founder of Genomic Prediction, a company that develops technology for advanced genetic testing, and others, have suggested that it might be possible to create a superperson with an IQ of even 1,000. Could IVF PGD replace traditional human sexual reproduction for many couples? In his 2016 book, The End of Sex, Harry T. Greeley clearly thinks so. He wrote, quote, "Sometime in the next 20 to 40 years, among humans with good health coverage, people will no longer use sexual intercourse to conceive their children." He writes that this will be not just possible, but cheap and easy, and that economic, social, legal, and political forces will combine to make this future not just achievable, but in his words, inevitable. Others agree. Joshua Abram, the co-CEO of TMRW Life Science, says 300 million people are going to be born as a result of IVF this century, driven by all the demographic, economic, and cultural forces you can imagine. Quite separate from sex for other reasons, there's good reasons to believe that people may increasingly rely on technology and science for procreation. Using IVF PGD is truly a game changer. It cuts the pain, time, and costs currently associated with IVF and greatly increases the number of eggs to choose from. At the same time, ever more advanced genetic science and artificial intelligence greatly expands the number of diseases that can be identified and screened out, or the attributes that can be selected. Together, these advances in human procreation allow parents unprecedented powers to ensure their children live long, healthy lives, and along the way, will greatly accelerate volitional evolution. There's a bunch of potential benefits from this, including a reduction in the number of people that suffer genetic diseases, more people able to have children, including the infertile and same-sex couples, children that are closer to what their parents would prefer, although parents may never be satisfied and children will always surprise, and expanded freedom to choose, which is a benefit in and of itself. No doubt, many parents will want to avoid IVF and PGD and reproduce naturally. But when you think about it, what's not natural about parents wanting to save their child from disease or wanting to give them every advantage? It may even be that parents who continue to expose their children to the risks associated with avoidable genetic and other diseases, and those who choose not to select positive characteristics, they may come to be regarded as uninformed or even failing in their role to keep their children safe and give them every chance of success. In addition, doctors, insurance companies, and governments will have a strong interest in helping babies avoid genetic and other diseases and the high costs associated with them. Even more fundamentally, evolution seems to be on the side of embracing IVF and PGD. As we showed in our video, Is Evolution Evolving?, the pace of evolution has always accelerated. Sexual reproduction evolved as a way to increase the speed of natural selection over clonal reproduction of single-celled animals. And IVF and PGD bring this evolution to a whole new level. The speed of evolution is greatly advanced as volitional evolution based on IVF-PGD replaces natural selection. This would constitute another major advance in the evolution of evolution and a great step forward in volitional evolution. We would indeed increasingly become the results of our choices. Said another way, if we fail to use this technology, we could actually doom ourselves to slower, less volitional evolution with potentially dire consequences. Rapid evolution may be necessary as human life expectancy increases and people wish to have children later in their lives, or to counteract the dramatic fall in sperm count we're currently experiencing. It's also possible that we'll need to evolve humanity to live on a warmer Earth, or in other ways to maximize our abilities to survive and reproduce. Limiting our ability to adapt limits our ability to survive as a species. For all these reasons, Greeley and Abram may be right, and more people may use IVF and PGD for procreation. There's a lot to think about here. When our team worked through the potential impacts of IVF and PGD on all the causes of death, we found that as profound as the effects could potentially be on humanity and health, they would most likely not have a major impact on HLE within the next 20 years. While the technology associated with iPSCs still has a way to go to become mainstream, this was most likely due to the fact that most of the changes in HLE resulting from the selection of more healthy children wouldn't be realized until those children grew up and lived to exceed their current ages of death, which would take decades. In addition, as with genetic and epigenetic testing themselves, while the risk of additional deaths was very low, adoption rates were more uncertain. Clearly, there's a huge amount to explore here, and we'll do that in our future videos. For now, thanks for considering how human reproduction could be revolutionized through the future use of IVF and PGD. In the meantime, please hit the like button below. Feel free to share your thoughts on this important issue. Thanks again for joining us, and as always, please do what you can to help yourself and others to live longer.